Hi, everyone. Today we're going to talk about machine learning workloads in scientific computing, how to scale them up, what are the challenges when you scale to distributed machine learning in large scales, and offer a different view of the problem from a data-centric perspective. So let's begin. Right. So machine learning is used pretty much everywhere at this point. Major companies in the industry, all major companies use machine learning to some extent in their pipelines. And more than that, we're seeing machine learning now rising in scientific computing applications, such as, for example, astrophysics and weather and climate, which is why we're here today. And what is happening now with these machine learning workloads in all fields is that the data sets and the problems themselves are rapidly growing in a very fast pace. And this is happening even more rapidly in scientific computing, where we have, for example, the ENES-10 dataset here for ensemble forecast systems by the ECMWF, weighing multiple terabytes. And in astrophysics, we see here in the slide that they're actually generating so much data per day that this is not something that you can train on. And so if you really want to run machine learning on these kind of workloads, you really have to access randomly these terabytes of data sets. And moreover, the models themselves are getting larger and larger, actually, so large that they cannot be fit anymore on a single GPU, for example. And so I would say that in scientific computing, and especially in weather and climate, we see that these problems are even more extreme in the sense that they require much larger sizes. So how do we use these resources efficiently so that we can actually perform machine learning on these kind of scales? So first of all, let's consider the computational pipeline. So what we are actually computing in machine learning. And here we want to start maybe with a more data scientific terms, right? So when we're looking at a machine learning workload, first of all, we have our model. That's the thing that we put in a sample, it outputs a prediction. And if we want to now improve that prediction, then we want to train that model. So for that, we can use any kind of optimization technique, like, for example, a stochastic gradient descent. And in order to do that, we have to propagate the outputs backwards with the error in order to compute the gradients. And this is what we call the backpropagation algorithm. And once we have all these gradients, we can now use them to update the weights in the neural network and then continue to the next sample or batch of samples. Right, so pretty simple, but in reality, and especially when you want to scale up to large workloads and large clusters, this is no longer everything that you have to consider, right? The sample is coming from somewhere, and there is some communication going on. Right, so if we now take this view and turn it into a more systems level view, then what we actually see, and this is more of a data-centric view, we can see what happens to the sample from the point where it's actually stored up to the point where we have to update all the weights. And so we can see that when you work with clusters, you sometimes you need to read that sample from somewhere. This might be a parallel file system or any other kind of storage location. This sample has to be decoded and augmented. So in images, maybe it's relatively easy, but when we're talking about data sets like weather, sometimes there is additional computation to be done. And then, of course, we need to evaluate the model. But afterwards, I mentioned that the gradient update happens at the end, but it really doesn't have to be, right? So we don't have to wait until we have all the gradients in order to update them. We can start updating them while we're performing the backpropagation algorithm. Those updates, when we're talking about clusters, they sometimes require communication, which would necessitate the use of some substrate like MPI or nickel, for those of you who know. And then this entire thing is a pipeline that runs for all the samples, and sometimes more than one stage of this pipeline is running. So really, this is a very complex kind of interdependency that happens between all parts of the system. And your bottleneck could actually be anywhere. It could be in the computation, which is something that we kind of are aware of, and more often than not, especially in cases for scientific computing, it's actually in the I/O, right? So reading the data. And what I want to do in this talk is to actually review all of these places and all of those stages here, and talk about what is currently done, what are the challenges, and what can we expect. We will start with the most basic of those, which is when you're evaluating a neural network, a single operator.
And so if we're talking about two-dimensional convolutions, like again, for the case of images, then we have many different ways of computing it. So we can do it directly. We can perform a data layout transformation followed by a matrix multiplication. We can even do a basis transformation for a fast Fourier transform or Winograd. But in the end, this is really well optimized for those exact two-dimensional sets and sizes. Actually, the sizes that would be a fit for ResNet 50 on ImageNet, I think, would be the most optimized set of operators. But if we talk about data that is sometimes a bit larger, so for example, in whether we have different pressure levels on top of the latitude and longitude data, so we really talk about sometimes 3D convolutions. And those, even though you could, in principle, apply all of these operations, they are not as well optimized as what we have for the standard, so to speak, operators. On top of that, there are new, the problem is beyond the problem of scientific computing for machine learning. And the problem of different architectures appears quite often also in standard machine learning. So one example that I'm showing here now is the transformers. So a transformer architecture is something that is a sequence transducer, so usually used for like translation. And what's nice about this architecture is that it can actually understand and attend like attention-based learning, which would be attending to different pairs of elements in a sequence, and not just like recurrent networks, which only take data in sequence, but actually see the whole sequence at once and pay attention to certain elements. This has been used successfully for text and even for visual classification problems. And so what we see in these kind of networks is that we have operators, and we have a lot of them. So we have a lot of different operators. So we also have compositions of operators. So we have the network itself here. So this is composed of several multi-head attention layers, each of which is actually composed of an attention sublayer. And then if you actually talk about the data that is passing through here, then between every one of those operators, and some of them are really simple, some of them are just element-wise operations, take that data, go back from the main memory of the GPU into the registers, do some processing, go back to the global memory again. And so what we have here from the data movement perspective is kind of a disaster, right? Because the data moves back and forth all the time. And this is basically given rise to the world of deep neural network compilers. So basically, the two problems that I mentioned, both that operators can be custom and that operators can be composed together, create a situation where we cannot now optimize every set of operators at once for every single size and every individual workload. So we take concepts from compiler construction, and then we normally, what we do is we take the deep neural network and we convert it to some static graph that can be analyzed. That static graph then becomes an intermediate representation that undergoes transformations. And then, for example, some of these transformations could be like if you have a transposition and another transposition right afterwards, these two can cancel out. So examples for these kind of DNN compilers would be XLA, which is used in TensorFlow and JAX. There is a Torch script, and now PyTorch FX, I think it's called. They have also another kind of optimizer. Intel has ngraph, and there's TVM. And so all of these DNN compilers are actually working in a way that they take the neural network and they perform these local optimizations between the operators. So for example, instead of going back and forth from the main memory to an operator, they can fuse operators together. Now, these local optimizations are really the next step in what we have now in optimizing deep neural networks, but this is also not enough. So as it turns out, these local optimizations can alleviate some of the problems that happen locally, but actually there are more global problems that can even further improve the performance. So then one thing that we do in our lab is to create another kind of intermediate representation. So it's called the Data-Centric Parallel Programming Framework. And what's different about this representation than the other representations is that actually what we have there is a graph-based representation that goes down all the way deep into the individual operators and don't just look at them as certain black boxes. So a transpose is not really a black box called the transpose, but actually opens up to see the data movement between the tensor before and the tensor after. So this then becomes much more flexible in that term. And we tried this approach on the transformer networks. And what we saw is that if you convert them to a graph, we could actually use this representation to study all of the characteristics of data movement within the transformer network. So we could dive deeper and then analyze each of the individual operators. And what we see is that actually the transformer networks are not really bound by the flops of the devices that we have, but actually by the data movement. So data movement is really the key bottleneck right now when it comes to optimizing the deep neural networks. And so we did even further studies. So based on this representation, we tried different configurations of each of the individual operators, and we can see that they vary as well. If you just change the data layout a bit, just transpose the data, these are 4-dimensional tensors, then you can get completely different performance, sometimes unexpected in terms of what you would think would be good or bad. So we use that to perform local optimizations, but on a graph level. With that, we can achieve good performance, outperforming basically the previous approaches. But also, what we could do when we have these graphs and with global optimizations is to actually try to find not just the best local configuration of data layouts, but actually a global optimization path that runs throughout the entire network and finds, let's say, the fastest path through the data layouts. And the best, you weren't necessarily going to take the best operator implementation for a specific operator, but you take the global best, which would mean to pass through the network as with the lowest latency for training. And this has proven to be very useful in terms of optimizations. We're talking now faster than what XLA or PyTorch can produce, but also faster than DeepSpeed, which was manually engineered for a specific type of a transformer, which is BERT. And so in the end, it seems like the path forward is not just to be doing local optimizations, but also global optimizations. And these transformers also, they pose a lot of challenges, also from the data science perspective. And for example, if we're talking about weather data, so these transformers that have these multi-head attentions, they take sequences of a certain length. But now when we're talking about weather data, actually it kind of is kind of a problem, right? To take the 4-dimensional data, which is latitude, longitude, pressure levels, and channels, and try to take that and turn that into a sequence. So how would we do that? There are many different ways. And so it's not necessarily the only way to take the entire thing and make it a token in a sequence. It would actually make sense to also run attention on specific parts of a single slice of the data, so not necessarily just time steps. However, there is a problem with that. So yes, it can achieve better accuracy. However, the parameters quickly jump up to billions of parameters when we talk about certain indices as your tokens. So when you take the sequence and use the different parameters, you can quickly get to networks that really don't fit on a single GPU. And so with that in mind, then we can go on to the next step and say, okay, now that we have a network, but it doesn't fit, how do we now scale it up to fit into more distributed environment? And so for that, there are different ways. Of course, I'm not going to go into detail about all the ways, but Let's say that, briefly overviewing them, the one that most of us know would be data parallelism, which is to take several samples in a mini batch and split them across the processors. Another way would be to take the operators themselves and kind of split them up. You can split them by channel or filter, spatially, or for different operators, you can have different kind of partitioning schemes. There is also another way to split up the data, which is pipeline parallelism. So basically take the network and then split it apart across layers. So then you can take the computation of one layer on one machine and another set of layers on another machine. And while you're feeding in layers into one, you're feeding in samples into one machine, the other one is already computing the results for the next set of samples. And so all of these approaches, basically there is no one size that fits all, right? So it's very data parallelism, but if you use too large of mini batches, you're going to affect your generalization. It also duplicates the parameters of all the processors. So with this replication, you again cannot fit a single transformer, for example. When you apply model parallelism, this is great. I mean, you can really split up the data however, or split up the activations however you want. It's really good for certain networks with large inputs. So for example, weather data of, let's say, global weather, that would be great to kind of divide that spatially. However, if we really want to run this whole backpropagation pass, then communication now becomes non-trivial. So it's not this one operation that sums up the gradients across all the nodes. It's something that is very layer dependent. And if you don't implement it correctly, if you don't pipeline exactly the computations in the right place, then you might hurt your performance quite a bit. Pipeline parallelism is sometimes simpler because now the distribution is very static. You have exactly one point where you send from one node to another node. And so if you have deep models and a small number of activations, for example, in transformers, the number of weights, the number of weights that you would want to exchange would cost, let's say, in the order of gigabytes. But if you only take the activations at a certain step, if you're talking about sequences of text, for example, this can be only tens of megabytes. So we're talking about orders of magnitude improvement. So pipeline parallelism can be great for reducing communication in certain models. However, sometimes this pipeline parallelism doesn't work well if you want to use the consistent model. So there is some kind of a bubble there for basically idle time for nodes that are not currently running anything. And so if you want to overcome that bubble, you would also affect generalization, because then you would make your model more asynchronous. So yeah, so partitioning the network is also something that can be customized directly for the problem itself, and these bespoke approaches can actually yield very high performance benefits. Another thing that is often overlooked, especially when we talk about scientific computing data, where our samples are not just 256 by 256 images, but sometimes they are, like whole galaxies and 512 cubes of double precision floating point data. And getting the data into the nodes that are actually computing the deep learning process is quite expensive. And so normally what's happening is that this process that I showed before is not something that happens sequentially, right? You don't just wait to finish with the next sample. You actually run in a pipeline. And when we run in a pipeline in data sets that are terabytes and tens of terabytes large, we're actually doing random reads on these tens of terabytes. And so even before we start decoding and pre-processing, we could have different stall reasons. And these reasons for stalling from reading from different kind of workloads, it could be just the number of active users on the cluster. So there is a lot of variability in the runtime depending on the I/O. And so one of the things that you could do, and this is work that we have also been doing recently, so I'm not sure if we can actually see the papers that are cited below. So one work is called HDMLP. So what is happening there is when we're doing deep learning, we're reading the data in a random way, right? But we still have a fixed random seed. What if we could use this random seed in order to predict, in order to know exactly which data is going to be read? So we did exactly that. So then we could even use that further And because we know which worker is going to read which data at every time, we can make some near optimal caching that would actually load the data and then exchange the samples between the nodes based on the knowledge of which samples they're going to read. So basically, because we have these random seeds fixed in advance, I mean, the random seeds can change, and of course, the process is as random as it can be, we can still use that, and we could improve the runtime of even the simple data sets. So even the image processing data sets can be improved from 1.3 times to 4 times speed up just by reducing the stall time. And you can see here that the times actually, they vary between framework to framework. And so, yeah, this I/O problem would also be and is currently a major issue, especially in certain clusters and supercomputers that are not built to read random data from storage, and especially not when you cannot have local storage in each node. So immediately after this reading and decoding process, there is a process of data augmentation that I mentioned before, and augmentation is very important for generalization, right? So if you take an image of a cat and you can use the same image but flipped, and now it's not exactly the same pixels, so you're less prone to overfit on that, but still learn the general gist of what a cat should look like. And so the same approach is already applied in other scientific computing data sets as well. Of course, it's not always the same kind of augmentations. But what we found in a recent work is that basically you can also change the way that you are augmenting the data. So instead of having different samples reading different augmentations of the same sample, we can have, with the same mini batch, within the same mini batch, have different augmentations of the same sample. So now we've also reduced the I/O costs of training. And not only that, we can actually improve the generalization of different problems. And with that, basically, you're with half of the epochs getting to the same accuracy in ImageNet. And so this is just some of those examples why training is not just the process of forward and back propagation. And there are many other things that I'm not going to get into. For example, for certain optimizations, you can redistribute the data. If you're training GANs, then you're having some non-trivial relationship between one network and another network. And the network, the load balance of the network can change over time. So all of these things really contribute to a more challenging environment to scale up with. And we are using, GANs for scientific computing data sets. And the problem is that the frameworks are not tuned to optimize throughout the entire process. So sometimes these things have to be done manually. So the last thing that I want to touch here in this pipeline is, of course, the communication. And this is, of course, when scaling up, an interesting problem. So we did mention before the communication of model parallelism and pipeline parallelism, but here I want to take mostly the data parallelism here into account, because again, this is the most common way to communicate, and also there is a lot of room to kind of play around with this, and there have been a lot of works who actually did that. So one thing that you should take note when you're creating a distributed learning environment is how you distribute the data. So we could go centralized with a certain number of parameter servers and have all the trainers kind of communicate with them. Of course, if you take a look at that from a data-centric perspective, this thing does not scale when you go beyond with the larger number of processors. There are other approaches, a decentralized approach. So for those of you who know with MPI, this is more or less computing the data separately and then running a collective operation. So all reduce, which means everybody is computing a collective summary of the gradients or the weights. And that could lead to lower communication requirements, or lower latency requirements. And really, MPI is great about that. You can have a lot of extensions that you can use in MPI to do that. Once you have that set up, there are other things that you could do. So you could relax the consistency of the parameters. So you don't necessarily have to collectively communicate the gradients at every step. You could go completely asynchronous, and so these works converge worse. Sometimes don't converge at all, but it's very important to remember. So this is the decentralized version, and this is the centralized version. So when it's a parameter server, it's very easy to kind of send asynchronously the data and then receive a new set of weights. When you do it decentralized, and I'll get to that in a bit, it's actually quite harder. You could limit the staleness factor, so how old your parameters are when you receive them. And this actually helps convergence, so we can only prove that asynchronous SGD works if you limit this the staleness factor. You could also use model averaging SGD. So instead of averaging the gradients, you could average the weights. And what you could do with that is actually to relax the averaging at every step. And this is a bit more robust to different kinds of averaging. So this is elastic averaging. You can, with elastic averaging SGD, you can, for example, average over more steps at once, and then that allows you to scale better because you communicate less. And on the far end of the consistency spectrum, there is learning. So basically, train multiple different models at the same time, and then at the end, when you actually want to make some inference, you just take the results of all these models and combine them together. So I mentioned before this distributed, so stale synchronous but decentralized SGD. So the question is, why would we even want to do that? So one reason to do that is actually because some of the data sets are imbalanced. So if we're talking about training over videos and training over sentences of different lengths, we actually have a load imbalance in our data, and we need to we need to take care of that, because otherwise our runtime would be basically determined by the slowest load or the largest load in a certain sample. So in a decentralized setting, we use this collective operation like MPI reduce. However, we're going to do that now in an inconsistent state where we don't have everyone computing the all reduce at the same time. So that's another recent work that we did, in which we created a family of partial collectives. So partial all reduce, where we have two versions, one where at least one of the processes has to participate, and another where we can actually see that the majority of the processes have participated in the all reduce. So the way that this works is, of course, detailed in the paper, but the end result is that you can now take heavily imbalanced workloads and don't depend on the slowest node, because now we only rely on the majority of the nodes to actually perform the all reduce, and the rest will be corrected later. And so this means that we can regain almost the same level of accuracy as the synchronous training, but actually with shorter times. So yeah, so there are other communication optimizations, sending partial data, so we can factorize the data and then send decompositions of that. We could quantize the data, so use fewer bits. This is also very common these days. You can even go as low as 1 bit SGD as long as you accumulate the error locally. So this is very important. So you can converge only if you keep the errors that you've aggregated by the quantization, for example. The same thing you can do for sparsification. You can now communicate not every weights, but only the, I don't know, top K largest weights, or there are other approaches here. And these all converge as long as you accumulate local errors. So all in all, basically scientific deep learning workloads and machine learning workloads in general, they change from problem to problem, right? We have large data sets, we have large samples in the data sets, but it's not the same as what you would expect with image classification and natural language. And the problem with our data sets is that actually we don't use or we don't scale up machine learning problems because we want this to be just faster, but because sometimes we just can't run them on a single GPU. So for us, it's kind of a necessity. Now, if we want to scale up properly, we need to take into account everything, like all the resources, want to utilize them the best way possible. So starting from the single GPU all the way down to how we access the data from the file system, right? All of this has to be the most efficient pipeline because in our workloads, it's not as well optimized as the others. And The thing is that it also depends on where you're running this. So different clusters would have different optimization schemes, different problems would have different parallelization schemes. There's no one size fits all. But for every part of that pipeline, we can optimize, and we can. And so with that, thank you. And if you have any questions, feel free.